doing quantum optics with free electrons, supported by my Marie Curie postdoctoral fellowship. Today's talk is gonna about two works I've been working on since I start my position here in April, which is the ultrafast Stern-Gerlach regime and the fractional charge. So long in short, the main contribution is I did first one, I finished a puzzle of diffraction regime in free electron system. Second is just a quantum simulator. So for you guys to know me better, because I'm a newcomer, you don't know me that much. I got my PhD in Shanghai University, but in the past 7 years, I've been frequently traveling from Shanghai to Basque, like a Rabi oscillation. So it's like a meme, but whatever. Yeah, better? Okay, thanks. And it's kind of funny because the first day I arrived Basque, I was also in the room in a workshop held by Kike Solano. So it's kind of like funny, it's my first official talk. Very emotional moment. So let's brief history of what I'm doing for electron laser. What is it? Okay, so back to the, let's say back to the 60s. We have laser, and yet we can have the free electron laser built by Madley in Stanford. So this is the fourth generation of physical platform to have free electron and manipulate it by laser. And later we have dielectric laser acceleration, which is connected to accelerator physics. But nobody deal with the system with quantum theory. But actually, this is quantum. So to the new century, Seville in Caltech, we had the PNUM setup, which developed the quantum theory for everything. And also the Spanish physicist Abajo in Barcelona built the theory for this job. And recently, we have quantum optics in free electron laser. It's basically used this technique to go to the strong light matter interaction for free electrons and see what quantum technologies we can play with. Why electron? While everything is listed here in one line, it is fast, it is easy to be manipulated, and it bridges all topics together. And it is not like a promise that, okay, in 10 years we will have it. No, it is now. The experimental techniques these days allow us to realize it physically. I will give you some very pioneering work in this topic. First is by Ido Kamina's group doing the imprinting of a light field with free electron. So basically he said, yes, PNUM process can be understood like a quantum random walk. Everything is fine. And he did it in experiments. Second is about the electron diffraction. Döners group in Germany doing the something similar to Kapitsa-Dirac effect, which I'm also going to talk a bit later. Basically, he discovered this fishbone-like picture. And okay, we have Kapitsa-Dirac effect. Everything is experimentally ready. So okay, here comes the question. Is it possible to derive everything in the same simple Hamiltonian? Answer is always yes. Oh, and all we need is a very simple minimum coupling Hamiltonian, which is a classical light at this moment, and with synchronization condition, which means the speed of the light should match the speed of the electron. And with some calculation, with some approximation, in electron, we have the effective Dirac Hamiltonian, which, if the electron is slow enough, then the structure, the curvature, gives it the Dirac Hamiltonian, and cut it into a two-level system. So what's the pseudo-spin? The pseudo-spin is the electron's momentum is slightly faster and slightly slower. And in this way, we have a two-level. Let's say electron qubit. A gentle reminder, what we had from AMO physics, because we usually compare this kind of setup to AMO, which is well studied. Okay, we have Ramanath, we have Bragg, we have Stern-Gerlach regime, three main regimes in atomic diffraction. So since we have the Dirac Hamiltonian, okay, we should study it to see if we have any difference, or to see if we can reproduce this phenomenon in electron system. Can we? Yeah, okay, people will say maybe it's the same, and we will see. First is the Bragg regime, that the electron is slow, or meanwhile the light field is not too strong. In this way, we will have a much larger than one Klein-Cook parameter, and in this way we see a typical behavior called the Rabi oscillation, and everything is fine. The same with Bragg regime in AMO. Also, when it is faster or the light field is stronger, it behaves like a Bessel function. We have very small Klein-Cook parameter. Again, it behaves the same like the AMO system. Or we can call it multi-level Rabi oscillation, or resembling the work did by Ido Kaminer. It seems everything is the same. Now we should check about the Stern-Gerlach regime, which is in quantum mechanics courses we all know, so I'm gonna be a little bit faster. Also, we did this in optics system many years later, before, which means, okay, we don't have a spin, but a pseudo-spin, similar to our setup, which we call it optical Stern-Gerlach effect. And now we're going to expect what we will have with the electron system. Can we reproduce optical Stern-Gerlach effect? Is there any difference? Which means we will have this kind like a phase diagram, but whatever. We will have Pinam, we will have Bragg, we will have Stern-Gerlach, exactly the same like we had in AMO physics, which means in Stern-Gerlach regime, we need the particle to be very well localized in real space. And with a gradient field, we will see the momentum splitting. But is it correct? We have the experimental setup, everything looks fine. We have a gradient grating, the light is illuminate the gradient grating and manipulate the pseudo-spin to change the momentum of the electron to see how the pseudo-spin looks like. And yes, we have the perfect splitting, everything looks fine. It splits, everything looks good. It seems there's nothing different, but is it? Let's see how good it looks like. Let's imagine it is a quantum simulator, then everything is fine. When the gradient is not very strong, it exactly fits what we are expecting from the theory. When it is stronger than the two-level system approximation, it's not that good, so it deviates a little bit. Everything makes sense. And next, the bottom figure says, okay, compared to Dirac, Hamiltonian, and our Pinam setup, the population is almost the same, so everything looks fine. We have a good simulator, and the simulator could be even better if we tune the electromagnetic field a little bit. Everything will be fine. Then let's say we get the electron more localized in real space, which means the width of the electron should be wider. Then, whoa, it's different. It doesn't split. Instead, it behaves like a fishbone pattern, which is the same diffraction pattern we had in anomalous Pinam effect, but here we no longer require the electron to be perturbed. So here we have something new. With gradient field, with a more localized electron, it doesn't have splitting. Instead, it shows a distorted Rabi oscillation, which is induced by the dispersion. So this is exactly what is different between the free electron quantum optics and AMO physics. Here's the gap. With and without gradient, also with the same Hamiltonian, we will have classical acceleration. We will have anomalous pinum if we perturb it. And this is the phase diagram we have. We finished the puzzle. And what we can do, we have Dirac physics simulator, which means, okay, we can do some quantum simulation of topological bond state that we get the Jacques-Rabi solution, and we can prepare it in the system and artificially create a kink structure. In this way, we will have the soliton solution, and it floats on the kink perfectly, even if when it is slightly offset, everything is fine. But if it is not a kink solution, if it's a Gaussian solution, then we have some dispersion. And why it is called fractional charge, it can be understood in the language of Gauss-Stern-Gerlach formula, and we can exactly calculate the quantum number, which is indeed a half electron. And why it floats? Maybe we don't need the language of quantum field theory to explain it. We can just do a chiral transformation and see, okay, the kink, it performs like a trap. So yeah, it moves the electron. This is the main two works I've been working since I joined here. And yeah, what we can do is we can do Klein tunneling simulation, we can do zeta-Bevegon, we can study the quantum tunneling time, the chiral anomaly, everything. Floquet, dynamical Casimir effect. Or we can say, somewhere we argue, okay, Yongcheng, you say you are doing quantum optics, but every light field is classical. You are not doing quantum optics, you are lying. Okay, then we do second quantization of the light field. And in this way, we will manipulate the quantum light by electrons. We will have some measurement-induced dynamics, which is exactly what I'm going to do in the next following years. But did I keep my promise? Yes. By second quantization of the light field, we have Janius-Cummings model, we have Davis-Cummings model. We see the collapse and revival, and even if the light is in a very strong, the coupling constant is extremely strong, we are in the deep, strong coupling regime, we still don't have those counter-rotating terms like to bring us to the quantum Rabi model, but into a multi-level coupling. In this way, we can have resonant single qubit gate and dispersive I-swap gate, allow us to do I-swap at any angle. And in this way, we will have universal quantum computing, and I will try to archive it maybe at the end of this month. In this way, we have a W state prepared by our setup in our new quantum computing model. And thanks to everyone, all the collaborators, European Commission, and my advisor for introducing me this beautiful country, Esquilicasko eta maite zaitu. Yeah, that's it. Yeah. Any question? Okay.
Hi. Thanks, Yongcheng, for the talk. In the last slide, you were showing some quantum computing, some basis states. So my question is, in terms of these electrons, what's the meaning of being in the excited state and in the ground state? In the case of these electrons.
Sorry, you have to do it slowly. I cannot hear very clearly. Sorry.
So you have there some computational basis.
Yeah.
You showed excited states, ground states, right? Yeah. You are using free electrons, I assume, as your sort of qubits.
Yes.
My question is, which is the degree of freedom in which you encode the excited state and ground state?
Yes, exactly with the classical field. So we have electron flying at a certain speed, everything is fine. And when it interacts with light, we have a grating structure engraved on the grating that gives a wave number, which means it could absorb a photon and being a little bit faster, or emit a photon to become a little bit slower. which does not break the phase matching condition, only slightly tuning of the speed, and a faster electron is in the excited state, and the slower one is in the ground state. Yeah, this is the degree of freedom we are talking about. Yeah, and of course it carries phase terms, so don't worry, everything is quantum. Yeah.
I also wanted to ask in the direction of this quantum simulation and computing that you said. So you said you simulate a Dirac equation, if I understand correctly. So could you, and the other said, yeah, I have a qubit and I can sort of couple it. So in both cases, I wanted to know, can you put in more than one qubit, more than one electron? Can you also simulate interacting electrons?
Definitely, exactly. You see the bottom right part? We can do 2 electrons on the grating structure, and in this way we have an I-swap gate. In this way, we don't have a Janius-Cummings model, we have a Davis-Cummings model, and we can extend it to a larger scale. There's no problem. All good. And we can couple it to, let's say in the language of quantum optics, we can have multi-mode instead of single-mode quantization. It allows us to simulate more complicated physics like gauge theory or something else, yeah, or Majorana physics. Everything will be fine, yeah.
Okay, if there are no more questions, let's thank all the speakers of the session again.
Yeah.